should I record to the cloud? Okay, Henrik apparently records.
Okay, Henrik records. Very good. Yes, Niklas and Niklas are now co-hosts. Awesome. Good. All right.
Stage is yours.
Stage is mine. Thank you very much. So thank you a lot for allowing me to come and present at this FP talk, so that I can pretend to be an FP researcher again, after not having published anything in the realm of functional programming for at least a decade. But that doesn't mean that I'm entirely rolling my thumbs, as we say in Swedish. So today I'm going to look at the expression problems, and the idea here is for me to present the problem, present some proposed solutions to the problem, and show you why they might not be solutions to the problem, and then show you some recent, fairly recent, depends on your time frame, student work, thesis projects that have tried to tackle this problem from different angles. So the expression problem, I think some of you should be familiar with this. So this is, as the Wikipedia page says here, it's a challenging problem in programming languages. It concerns extensibility and modularity of statically typed data structures. Okay, so first of all, extensibility and modularity, those two things are not the same thing, and I'll get back to that. We see different approaches to this. And everything I'm going to say is within the topic of static type. Because if you can do things like dynamically changing prototypes or whatever, you have all kinds of extensibility, and you don't have this problem at all. So the whole point of it is that you want to retain static typing while you enable extensibility. Okay, so the goal is to define data abstractions that are a data abstraction, right? It should be extensible both in its representations and its behaviors. Okay, what are representations and behaviors? Well, that depends on what kind of a programming language researcher you are, what you normally call them. In a functional programming setting, we would probably call them the constructors. More generally, we might call them the variants. That's the representations, the different forms that values of a data type can take. And then we have behaviors, which functional programmers might want to call functions. And other kinds of programmers might want to call them methods. But we're essentially talking about the same thing. Okay, the point here is that we want to be able to add new representations and new behaviors, okay, without recompiling and while retaining static types. Okay. So you might immediately, if you're aware of this problem before, you might have considered these things before, but if this is new to you, you might immediately start to think, well, okay, Haskell or whatever other functional programming language you prefer, what's the problem? What can we do? What can we not do? So let's look at that. Okay, so first of all, here's a quiz, and it's deliberately formulated the way it is. What's the difference between an object-oriented language and a functional language? I ask my students this.
But it's
yes, exactly. The question is asked incorrectly, right? This is not a dichotomy. We can have languages that are both object-oriented and functional, etc., etc. Okay, but my students can answer this. They might not understand that the question is asked incorrectly, so they give answers if I ask them this, right? So what do they say? Well, okay, so let me phrase this in a way that you might find palatable. Okay, what are typical features that we might find in the languages that we somewhat sloppily tend to call object-oriented or that we tend to call functional? And again, this is not a dichotomy, for categorizations. What would you say? What are defining features?
classes and data types.
Classes and data. Okay, so classes would be object-oriented languages, and data types would be functional. Yeah. Okay, good. I completely agree. Although I would use the term objects rather than classes. Okay, because you don't actually need to have classes.
But you talk about static typing.
Yes, I do talk about exactly so. So whatever language that we talk about that we might call object-oriented, it will have objects as it or data representation. Okay, and then we have common interfaces. They might be in the form of classes, they might just be interfaces, but they somehow define a type as a specification of the behaviors expected of all the representations or variants. I'll try to use a variant of this type. Okay, so different classes of objects in a language that supports classes like Java, for instance. We define different versions of this common interface, and we can do that independently of whatever other existing implementations of the interface already exist. Whereas functional languages have data types, several algebraic data types to be more specific. And these are then a specification of a set of representations or variants, right? These are the constructors of your data type in Haskell. And we can add functions rather freely that operate over this type. We might specifically in Haskell say we do pattern matching over the different constructors. And we get different behavior. So, and different functions, we can add them irrespective of one another. Well, unless they, of course, base on one another, but we can define completely separate ones. So we can define new behaviors. And these two different ways of using data representation, when we talk about extensibility, they can lead, we can view it as that they are two different orthogonal dimensions of extensibility. Okay. So before I explain that further, let me just say then here that this, taking this role, this approach to it, means that it's not a problem to have functional and object-oriented languages. Scala, F# have both objects and algebraic data types. Even a language like Java has enums, which are not actual algebraic data types. They're like pseudo proto versions of that, but it's perfectly fine to have both kinds existing in the language at the same time. Okay, so these orthogonal dimensions here, we can visualize this by looking at what we call the dispatch matrix and looking at how these two orthogonal dimensions become a transposition of this matrix. So what do I mean by that? Well, okay, this is taken from, so Johannes might recognize these slides. This is from an object-oriented design course where I've had the privilege of teaching students for many years that have read both functional programming and basic object orientation. So you can actually talk to them about these things, which is super fun. So let's assume that we have a data type as defined by this, right? And then we have a number of behaviors that we expect this data type to support. And we have a number of different representations of this data type. This might not be the perfect way to represent polygons. Don't mind that. Okay. It's just an example. So for each of these, we would have a separate behavior saying for squares, how do we translate a square? How do we translate a rectangle? How do we scale a square, etc. Okay. So if we were to go to an object-oriented language and use objects as our basis for data representation, then it would look like this. Okay? We would define a type, having some behaviors specified, and then we would define one after the other a number of implementations of this type, which are separate from each other, independent of each other, and defined in different files. Okay, so it might look something like this. We define an interface polygon with these methods. This is Java. And then we can let the square class implement this interface. We can let the rectangle class implement this. And if at some future point I want to introduce like hexagonal polygons or whatever, I can add more things. Right. Okay. So Kun, you look.
Oh yeah, I have a question. So you decided to let rotate, translate, and scale return a polygon instead, and then you lose type information.
Yes. This is, I could have used, maybe void would have been more object oriented in nature, that is actually update the
But
state.
maybe then it's not easy to compare to the functional code, which would, yeah.
It's not the primary purpose of this slide anyway. So I grabbed these slides from my course material, and there we do talk about these different versions. But for what I'm going to present to you today, that doesn't really matter. Yeah.
But you could, with like proper variants, you could make all of the square implementations return a square, right? Then you wouldn't necessarily use the different one.
No, exactly. I could have written square here in the square implementation because it's covariant in the return type.
Yeah.
Yes. So that would have been fine. I just didn't do it. But that's kind of a subject. The point here is this. The point is that we can extend freely with new variants. Okay? And if we have algebraic data types, we get the transposition. So instead of going this way, we go this way. So in Haskell, we instead then define a data type and we enumerate the expected variants, namely the constructors. And then we can define freely new functions, behaviors over this data type through pattern matching in this case. And we can go on and we can add scale and we can add get corners and whatever other things we want to do. So if we look at the matrices again, like you see here we have free extensibility in that direction. We can add more columns. And here we have free extensibility in this direction. We can add more rows. But we don't get the other, right? So for the purposes of extensibility, traditionally object-oriented languages, we can freely add new variants, but the set of functions that we expect over those variants is fixed. Okay? There's some caveats, I'll get to that, but this is like the general trend. Okay, so if we want to add a new function that should be applicable to all the variants, we need to go in and actually change the source code, and then we compile. Okay, so this breaks the expression problem as this is not a solution. And then conversely, in traditional functional programming languages, we can freely add whatever new functions we want. We can do dispatch over different variants using pattern matching. But the set of variants that we've enumerated in the data type, that is fixed. We cannot add new data types as we need if we need to extend new versions. Okay, so again, you can see this. We would have to go in and actually change the data type, and then we would get type errors for all of the methods that previously worked over this, and we have to go in and fix all of them as well.
So in the first problem, you mean that you have a language where you cannot define a function outside the classes where the...
No, that's one of the caveats. Okay, so that's actually this one, right? Because of course you can define functions outside of the existing ones, but either you can only define them in terms of the functions that are already part of the type, or you have to define them using, in a sense, and I'll get to that, explicit encoding of pattern matching, in which case you have to lock yourself to a set of variants again. This is actually the visitor pattern, and this is something that I'll show in a second, right? So I will forever wonder, no, I won't wonder, but I will forever bemoan the fact that people within the communities don't talk to each other, and that the visitor pattern is called the visitor pattern and not the pattern matching pattern, because that's exactly what it is. It's a way to implement pattern matching in an object-oriented language. Okay?
Why is it called visitor pattern?
Because the function, in order to be able to do dispatch on different variants, you have to encode it in such a way that the function, the object containing the function, is passed into the object it's supposed to visit, so that the code can be executed from within that object.
Okay.
These are fine details. We can look at the code. Okay. And there's also object algebras, which is like one of the things I'm going to get into today. And again, in functional programming languages, there are also like proposed solutions or tricks and fixes that we can look at. Like we can use functors, fixed point recursive structures. We can define variants, data types that are inherently and explicitly extensible. And I'll get to all of these. So before I do that, like, okay, we're all researchers here, so we might not need a motivating example. It might be fun to look at this just because it's a fun thing to look at. But I mean, there are some real world applications for this. And the most commonly used motivating example is abstract syntax trees. And this is exactly the use case that I have and that has made me interested in this and digging into this in various ways, right? Because I have a compiler. We'll see that in a bit. And you might want to use different sets of constructors or variants, different sets of nodes for your AST in different compiler phases with different auxiliary information attached and as annotations and so on. So the running examples that I'm going to use will be of this kind, but there are also other examples. And if you come from the object-oriented world, you would be talking about embedded domain-specific languages a lot. I guess that's. In fact, when I Googled around for this, Obsidian was one of the things that came up, where you have like modular data types. Some stuff in computer graphics systems and product line features in feature-oriented systems. I don't know much about that. I just put it up here to show you that there are applications. I will be focusing on this part. So we do want to be able to have this. And then there are a number of solutions proposed over the years. So data types a la carte. How many of you have heard of this? How many of you have?
Oh,
How many of you have read the paper? Well,
wait, you haven't read it?
No, sorry.
I mean, this is a very nice paper. It is a functional Perl, as it says here. And the paper says it describes a technique. Oh, what happens now? I'm getting ahead of myself. A technique for assembling both data types and functions from isolated individual components. Okay, that's an explicit way of saying modular data types and functions, right? From isolated components. So let me look at this, right? So which one should I have? I think I should have this one. Yeah, okay. So can you see this?
Yes.
Yeah. Good. Okay. So the first thing to notice is this line. Type operators, derived functors, flexible instances, multi-parameter type classes, functional dependencies, scope type variables, type families, flexible. Oh, yeah. Okay.
I know some of those.
Yeah. Yeah, I know what all of them are as well, but and I'm not going to go into them. Just notice that they are there. Okay. So this is what a standard closed abstract an algebraic data type for a very small toy programming language would look like. Okay, so we have data types for expressions and we have literals and we have addition. Okay, and then we can define an evaluation function over this through pattern matching. Okay, but this is a closed data type in the sense that we cannot extend it in any way. So then even predating data types a la carte, there was a paper by Oleg Kiselyov et al. Which proposed something called tagless final or representations, where instead of defining an abstract, an algebraic data type, you would define it as a type class with builder functions within it, so that you can use it to build different kinds. And then you would have to encode evaluation as instances over some representation type. And then you can add other instances using a different representation type. And then you'd have to explicitly build using these smart constructors for these things, right? Really pretty.
Is this legal Haskell to not indent?
To not indent, no, that's probably my fault.
Okay.
Yeah, no,
You don't have
these
to.
need to be indented. I copied this from their paper.
So this only allows you to write like catamorphisms, right?
Yes, and I'll get back to exactly that point as well. This predated and influenced the data types a la carte paper.
It is also called algebras,
Yeah.
like what you call this.
Yes.
The class.
Yes,
is
these are algebras. Indeed.
expression algebras.
Yeah.
Okay.
And the point here was not to enable extensibility or modularity, but to get rid of the explicit data type representations. So you could build these things and avoid having a representation.
Right,
But-
and if you want to change the type, sorry, if you want to, there's two functions you have there, right?
Yeah.
R and something else.
Yeah.
If you have the expressions already, and then you have to recompute the whole expression.
Yeah.
So if it's expensive to make the expression, you do
Yes.
that computation twice.
Yes.
Yeah.
I'll
Okay.
get to that as well. You're absolutely right. Right. Okay. So I concatenated several files in one here. So okay. No, actually, I concatenated the same file twice because here is where I'm going to continue. So the data types a la carte version of this, it would be based on functors. So instead of a type class, we would define for each variant that we want, we would define a separate data type, which is a functor. And then there's this thing called a coproduct. This is like basic in data types a la carte. You don't define that every time, you just use it so that you can combine these functors and get something that contains the set of variants that you want. So this is actually modular. You can pick whichever ones of these defined variants you want, and you build a chain of them using the coproduct to get like your set of variants that is then defined. And then you have to close it explicitly with this fixed point operator to get something you can actually work on. So then we could say, well, we have an addition function that takes one of these and another one of these and returns yet another. So we can build expressions like this. We can use some smart constructors as well, so it doesn't have to be quite that verbose. And then we can fold, and this again, catamorphisms. We can define folds over this algebra that we've defined for instance, we can then build an algebra for evaluation or for printing, and then I don't actually have the version. It's probably at the very end of the file where I have the main, which uses fold fix and one of these algebras to become the eval function that we see. Yeah, but without the indentation. Sorry about that. I think you can. I think you can follow that. Right, you can plug eval alg into this hole here. Right. Okay, so that's pretty, and then we can. That's. Didn't I have? Sorry if I put these things in the wrong places. Did I have different examples here? This is comp data. So yeah, so this is again, this is data types a la carte as implemented in the comp data library package, where we have again these variants, and we can define types with them, and we can create these smart constructors. That's what I was trying to say before. Sorry, my mouse is playing tricks on me. So then we can define an eval function using and in this library, the fold is called the kata, and you apply it, and then you get an evaluation function. And then separately, you can extend this with other variants, and then you just have to introduce the
Wait, what does that mean? Extend category expert with?
Yeah, no, I've mixed up the
Like
files.
you
I'm
added
really,
PDF or-
yeah, I'm really sorry about that. This is not at all the same one. I concatenated these files. This is the one I wanted, right? This is the one that should go here. So we define a new functor for the new version. Then we extend the signature with yet another coproduct. We introduce a smart constructor, and then we introduce a new point in this algebra for working with these negations. And then this works, this application of kata to evalualgi works for the extended data type as well. And you can, yeah, so I'm sorry, I'm really confused now because I thought I copied and pasted this from various sources that I've had so that I could give you only the things I need to show you, and then I've apparently mangled up all of these things. So yeah. In any case, I think you understand the idea, right? But the point here is that we can define these data types and functions, and we can combine them using these coproducts and these algebras from isolated individual components. Yes, okay, that's true. And the paper is really nice. The paper suggests that this is really easy to do. But when you actually try to use it in practice, there are challenges. Okay? And one of the major challenges is that, well, compare this, just this simple bit, this bit, to the very first thing that we had. Okay, now I know file, but now I know which file to go to. With like this, which is how we like intuitively want to define our data types and our functions. And now suddenly we have to introduce all of these things and what to understand coproducts and fixed point recursion over data types. I mean, okay, maybe you can just tell someone this is how you do it and they will do it. But
and one argument is also that this is not the way we do data types. So you have to know beforehand, I'm going to want to extend this data type maybe. And
yes, exactly. And then another challenge is then that, this approach, it only works for catamorphisms. It only works for the folds where you can actually dispatch on the type information of each of these variants. And in the paper, there's some speculation that says, well, this should work similarly for anamorphisms, so we can unfold and build things, and no, it doesn't. I've tested it extensively, and I've communicated with about it, and he also concludes that no, it doesn't work. So this is not true. And a concrete example of something where you want to use this is then if you have a parser that wants to build an abstract syntax tree.
That's a great example.
Yes.
That's so hard.
Yeah.
Because not only do you have to add the constructor, you also have to go into the parsing algorithm and
exactly.
Wow, that's a great challenge.
It's a huge challenge. And then there's also some challenges which is partly fixed by this comp data, but as the paper presents things, there isn't a single canonical representation of these coproducts. So you have to make sure to always build your coproduct trees in the exact same way. But you could, if you have, like you've built one set of variants, let's say containing so let's say literals and addition, and then you want to add another one which introduces multiplication and negation, and then you want to combine these two. Well, you couldn't just build the coproduct of them because that would not be the same thing as the tree where they're all in the chain. I'm not sure if that made sense. If it didn't, just the whole point of all of this is this. I could never tell our bachelor students that this is how we build extensive.
Isn't this also a problem, like say you want to add let and variable to your expression language? Then suddenly you also need new structures, like
Yes.
the environment
Yes.
or the evaluation function changes in its signature, so you
Now you have to define a new evaluation function with a new signature, and then define a behavior for all of the other ones. But yeah.
I want to defend this a little bit. Cut me off if you don't have time for this. But
sure.
so to me, the nice thing about these kind of papers is not like, oh well, you just use Haskell and you just this big brain catamorphism full thing. But now we understand how it works, so we could make a specialized language where we hide also stuff like this, right?
No, absolutely, and that's exactly where I'm going, right?
Right.
So I am absolutely not bashing this paper.
No. Yeah.
So I really like this paper. It's one of the papers that have influenced me the most. I'm just saying this is just a theoretical, if you like, a foundational building block for creating something that actually works, because you could not use this in practice. Okay, so and then there are people on the other side, if you might say, which reach very similar conclusions. So there's a paper called Extensibility for the Masses, suggesting that this is something that everyone can use. Practical extensibility with object algebras. Okay, so this paper presents a new solution to the expression problem. Awesome. It works in object-oriented languages with simple generics, but of course in our world that just means parametric polymorphism, because generics in Java is what we call polymorphism. So it's not actually generics, but the point here is like, we believe that object algebras bring extensibility to the masses. Object algebras work in mainstream OO languages, and they significantly reduce the conceptual overhead by using only features that are used by everyday programmers. Okay. Now this is really the point of all of these papers that I present that I'm bashing, because I think all of these papers are really nice, but they all seem to say this is a really simple solution that everyone will be able to use. Okay, so let's look at this in practice then, because this is also inspired by the tagless, final, spineless, whatnot. Yeah, I don't remember the different versions of this. Right? Okay, so here we have first, like, here's an abstract syntax tree in Java, where we define each of the sorry, I don't like my mouse. We define a data type for expressions as an interface. So this defines the type, and we have the behavior here because we're doing a visitor pattern. We need the accept method here. And then we define classes for each of the variants. So we have literals and we have addition. And these then implement these accept methods so that they can accept a visitor that they can then apply this method to, and you get dynamic dispatch, and you can actually dispatch on different variants. That's not the point. The point is here that this is just a backdrop. This is just an implementation. This doesn't give you extensibility. This just gives you pattern matching. But then pattern matching as over an algebraic data type in Haskell, you're fixed. You can no longer extend the data type. So you can define different visitors through implementing this visitor interface, and they can then pattern match and dispatch. I want to do this if I encounter a literal. I want to do this if I encounter an addition.
So the argument that we used against the Sweester's paper, you can already use against this, right?
Yes.
There's so much overhead to do.
Oh yes, and I haven't even gotten to
exactly.
I haven't even gotten to object algebras. This is just a visitor pattern. And I mean, the object algebras, they are not necessarily more boilerplate than this, but still it's on the same order. So the point is very similar. You might say they introduce these kinds of constructive functors, if you wanted to use that language. But the point is similar. You define a type parameterized over some other type, which is then the representation that you're after. So you're parameterizing over the concrete representation. So you have constructor functions, as they call them, or builder functions. So these just tell you, I can build you a literal in some arbitrary representation if you give me a number. Okay. And we can then instantiate this for different representation builders. But then we can, let's see, this is expand, yes. So this defines the algebra, and then we can implement this algebra for, say, evaluation. Sorry. Here, right? Okay, so if you give me an integer, I'll just give you the integer back. If you give me an addition, I'll just compute the addition and give you the result. Or we can print and we can do different things. Okay, so then you could construct these composed expressions in this way. Very nice, right? It's almost as easy to read as the comment at the end. P plus 4 is 1. Okay. And this is very simple. I haven't even gotten into, like, if you extend the algebra to add another data type, then you would have to extend the xalg interface with a new interface and then introduce yet more builder functions, etc. Okay, so it indeed only, as they say, it only using features that are used by everyday programmers. Okay, yeah, sure, but maybe not in this way. And maybe they got this idea themselves because there was a follow-up paper a few years later called Feature-Oriented Programming with object algebras, where they say while object algebras excel at defining modular features, the composition mechanisms are still cumbersome and limited in expressiveness. Well, yes, they are. And what do we do then? Well, in this paper, we leverage two well-studied type system features, intersection types and type constructor polymorphism. And then suddenly we're way gone from the world of everyday features used by everyday programmers. Okay? And again, I don't want to bash these papers. From a theoretical point of view, they're really nice. They're really good. It's just these formulations that I'm bashing, right? No, don't oversell it. Okay, so, and this also comes with a bunch of challenges. That means these are not really solutions to the problem. Okay, so these also have no canonical representation. And you said that earlier on, Kuhn, like every time you use this, it's ephemeral. It's built and constructed and folded at the same time. So you don't actually have an AST that you can do multiple passes over or do other things. And if you were to do that, you can create a builder that creates an AST, but then you're back in the non-modular world. And then what if you need operations that can work over different kinds of representations, say expressions and statements? What do you do then? Well, then you need to go back and reparameterize all of the expression algebras over statements as well, even though they might not in turn contain statements. And if you try to scale this up, you very often end up with having to introduce explicit type annotations, which in Java we are not used to doing. And everyday Java programmers might not even understand what the type annotations are or why they need to use them and where they are, etc., etc. And then, I mean, this ties into what Andreas pointed at, like there are other kinds of operations you might want to do where so that was not exactly what you were saying. You were talking more about the different kinds of expressions with different structures. So that might be more like that. But like there are operations over this tree that are inherently not compositional. You can't build the result out of the results by composing the results of the sub-expressions. And then this doesn't look so nice anymore. Okay, so if we are at all going to use this for anything practical, even small scale, I don't feel like I can explain object algebras to our bachelor students. This is something that I've considered introducing as part of my lecture, but I'm like, no, they're not going to get it. They struggle understanding what parametric polymorphism is. I have no idea what that is.
Well, in 50 minutes, the meeting is over.
Yeah, exactly. So, okay, so these are approaches to having modular data types. So maybe we don't actually need modular data types. If it is the fact that our canonical example here is to build abstract syntax tree that we can vary, well, maybe we just need extensible data types. So the analogy here, if modular data types means we can compose things like Lego, we can pick the pieces we want and put them together the way we want them. Then like everything starts from scratch, we can pick exactly what components we want. But extensible data types, the best analogy I could make was, well, okay, you have a mobile phone, you have something stable that you start with, but then you can add on to that because you need more functionality in various ways. So there is a base data type, but then you can add variants or you can update and add things to existing variants.
And those variants cannot be added to some other data type.
No.
Like you would do with the modular data.
Yes.
Data.
Yes, exactly. And this approach was taken in a paper called Trees That Grow. Some of you may remember Cheyenne, who was here. He was a master student and then a research assistant for a while. And then he went on to do an internship with Simon Penney-Jones, and he started but never finished a PhD with Phil Wadler. But during his internship with Simon Penney-Jones, they wrote a nice paper. Again, I'm not going to bash the paper. It's a nice paper. I recommend you read it. It's called Trees That Grow. Abstract syntax trees that grow in this case, because you can add things to them. So they say we started the notion of extensibility in functional data types. I've called that right data types, but maybe there's a match there. And specifically, they want to address a particular form of extensibility. Okay, so we're not in the territory of full modular data types. We're looking at a specific form of extensibility. And they want to use type level functions and pattern synonyms. So maybe it's not so bad. We just use some advanced features, but then they say to make it convenient in practice. And I think you can already like foreshadow where I'm going to end up with this. Here is the first of the student projects that I want to introduce you to. No, actually, let me first show you I'm scared now, and I'm going into this and see where I might end up. This is probably not the one. No, then we'll go for the other one. Here, trees that grow. Right. Okay. So you have a data type for expressions. This one. And then you define the variants as you normally would. But instead of saying just lit int and add exp, you now have this x that you parameterize over. This is a representation witness for what version of the syntax tree that you're going to use. And then you have these extension fields to the various variants. And this one didn't actually have an added. Okay. This is not good. I'm terribly sorry about this. There should have been yet another constructor here, which says something like Something like that. There. So that you can add a completely new, if you wanted, a completely new variant or a set of variants even by parameterizing over.
X is defined nowhere. Am I missing something? So the
Sorry,
structure
no.
name is
Yeah,
the type name.
it's me that is.
Right.
I'm nervous because my pre-cooked dinner came out of the oven in a very strange way. No, that's a good point. Yeah. So and then you define these data types, type level functions, which are the different representation types. Here they are using the void to just say, well, we just have lit and add, but you can add more ones later where you add source positions, for instance, and then you can build things in this tree and evaluate by breaking it down. Okay, but there's still some boilerplate here. So I had a group of students actually stress test this in like full on, not just toy examples. Because I have a compiler, the Paragon compiler, and this talk is not about the Paragon compiler, but the Paragon compiler is written in Haskell. Oops, sorry, wrong direction. Okay, so, and here they say in their abstract for their report, its current implementation is monolithic, making the compiler challenging to develop. Yes, I did not have a better way of doing it. I built one big chunk and an abstract syntax tree containing all possible variants of all possible bases. Okay, so they identify then the representation of the abstract syntax tree as an essential design aspect and emphasize extensibility, right? And then they go on and say, based on the programming idiom, trees that grow, we implement an extensible abstract syntax tree in Paragon's compiler. Okay.
Oh wait, so the Paragon compiler is implemented in Haskell, so they use this design Penn Jones and Cheyenne paper in Haskell,
Yes.
not in your language.
No.
Okay.
They exactly. The fact that it's this Paragon is absolutely irrelevant. They're doing everything.
They took some random compiler and
Yeah.
okay.
Very random compiler. And then they say, we observe that our implementation introduces a substantial amount of boilerplate code. That's an understatement. And then they alleviate the issue. They employ several methods for generic programming, like template Haskell style. And they conclude that this AST implementation is extensible, but complex. And that's like really British sarcasm, understatement, complex. So yeah, I'm not going to go into that now. So this is basically saying the same thing. Okay, so the key takeaways from this is, yes, it was possible. They spent 5 months doing this, and they came up with a possible extensible data type.
Okay, but they already knew beforehand how it was going to be extended.
No, they chose trees that grow.
Well, but I mean, you had the monolithic data type. They went back.
They knew which compiler phases they needed to support.
Right.
Yes.
And how easy it is to add a new one that they didn't think about. Yeah.
Good question. I don't have an answer. Okay, so but they could do this so that they could use the same abstract syntax tree, but rather different versions of it for different passes in the compiler. And then they concluded that there's a huge amount of boilerplate code to get all of these things to fit together, and it's not easily readable. And they did use some generic programming techniques, and that did help. And it did make the code easier to read, at least if you understood how to read template Haskell code, but only to some degree. Okay, so the conclusion here was, and they write this in not so many words, it is possible, but it's not feasible. So this paper that was originally pitched as make the Paragon compiler more modular was in the end a case study of trees that grow that came to the conclusion this was the wrong way, but at least now we know that it was the wrong way. So, and also this really also requires some big brain capacity. In fact, 5 of the 6 students in this group said, we're very lucky to have the 6th person in the group. Otherwise, we would have no idea what we were doing. And these are bachelor graduates.
So here you were, he was demonstrably able to teach these bachelor students though, because they.
Yes, I mean, there was one stellar student in this group who really did a big part of the work, both in actually implementing, but also getting everyone else on board and bringing them along. So it wasn't a wizardly programmer just doing his thing. He actually made the others understand. And that was cool to see. In any case, I was not happy, and I pitched this master thesis proposal a number of years back. I'm not going to go into the details. The point is, it touches on all of these things that we've talked about: object algebras, data types, and hierarchies. But these works have weaknesses and drawbacks, and have not seen any real adoption. Okay, so I also then had a couple of master students working on this from this proposal, composable data types in Haskell. This is their report, a syntax for composable data types in Haskell, a user-friendly syntax. Okay, so, and here they also point to something. There exist a number of different approaches to solving the expression problem, which have different qualities in expressiveness or in simplicity. That's a very nice and diplomatic way of phrasing that. And then they also say, in this thesis, we designed a syntax that acts as a solution to the expression problem, abstract away some syntactic overhead, and here, our syntax provides several improvements compared to existing solutions to the expression problem in Haskell. I actually think this is needlessly humble, because I think they did more than that. So Andreas was the examiner for this project, and I think we were both quite intrigued with what they'd done. Correct me if I'm wrong, that's fine. So let's see. What they did was they went to the drawing board and asked the question, how do we want to write this? Okay. So they introduced something called categories, which are basically, I shouldn't say kind annotations, but they identified that there was a need in expressiveness to be able to categorize different variants as belonging to different categories. So basically a type of types. But it's not necessary. You could do it entirely modular and pick whatever variants you like and put them together. And then you would write your eval function, for instance, just the way we would expect. And then you can add, so this is the code that accidentally ended up that you were all confused about, including me. You could extend the category with a different kind of expression, and then you just have to add a new case. And it doesn't have to, this could be in a separate file. And you can add functions separately that can also live in separate files. And you could define subsets. Say, we only want these. Okay, and then you enumerate exactly the variants you want. And all of those functions above, they still work. And these...
Wait, they still work, but if they use those constructors to construct things.
If they use those constructors,
Yeah, so
these constructors as defined up here, the lit add and
if I say simple expert,
yeah,
and then I have a function that doesn't only destruct them but also builds expression.
Mm-hmm.
Is it guaranteed that they don't use lit and add anymore?
Yes. Okay. I don't remember the details. This was 2 years ago. So let me just say, so the way they implement this, let's see if I can, yeah. The way they implemented this was as a transpiler. So here we're back in the world of comp data, which is the implementation of companion or data types like that. So here everything looks exactly as you would expect. If you had written this by hand, we're using data types a la carte. So then you get, a lot more code for
And
that same
it's
stuff.
just as modular. And the transpiler is,
Yes.
okay.
It has exactly the same modularity as data types a la carte, but a syntax that is much more intuitive and easy to use. And you can like criticize specific design choices here. That's not really the point of the paper.
I would like to ask you to
wrap
it.
up. Yes, indeed.
Yeah, I
So
would like to ask you to wrap up.
Jenny would like. Okay, is she here even? Yeah, no, she wants to talk to me. But still. Okay, so final remarks. There are a lot of solutions proposed, but I would strongly argue that there isn't actually a solution such that we can say that the problem is solved. It is still an active research field. There's interesting developments. I don't have time to involve myself too much, but if any of you think that this is fun and we can have a discussion with around it, then by all means, grab me. I have some references. I also put in a list of things happening in the area which build further on these, which I've only managed to skim very briefly. And then some references to these theses, which I think are very nice. Would recommend you to read. And there's yet another thesis, which actually I didn't find, which is then a truly object-oriented general purpose programming language, where it's also a proposition of mine to build an object-oriented language that does not have subclassing. And that's a completely different story. And I can talk about that some. Thank you.
Yeah, this is a fun. Thanks for the fun talk. There was a thesis published? Was it a published paper?
So the ones that I showed you at the end there, they are published in the Chalmers open data repository.
Right, but they didn't turn it into a paper.
It's not been turned into a paper, and I still think we should.
Yeah,
But
sounds worth it.
they've gone on to do industry gigs.
They
So
could be a co-author.
They could be a co-author.
Yeah.
I haven't given up on the idea of doing that.
Okay.
It's a really nice paper. It could be a really nice paper. Okay,